Hi, round two. This is section 3.4. We're going to be talking about lipids in this video. So lipids are not really monomers, polymers. They're not really long chains of anything. We can have long hydrocarbons in our fatty acids, but we don't have one lipid attached to another lipid attached to another and another, like we did with the carbohydrates and the sugars attached together to make starch or glycogen or cellulose. A couple of the takeaways that are really important is that all lipids are hydrophobic. They do not like water at all. And what kind of impact is that in terms of their electronegativity with the atoms that make them up? It means that they share the electron and their covalent bonds very nicely. The electrons spend equal time around each of the atoms. It doesn't hang around one and then go over here and hang around another. So there's no polarity in the molecule. So they are hydrophobic, nonpolar, and do not like water. Okay, we're going to talk about three kinds: fats, phospholipids, and steroids. Fats are made up of glycerol attached to three fatty acids. And I'm going to I think it's easier, honestly, to see the diagram. So we'll take a look at this, and I will draw it as well. This is the beginning of making a triglyceride. Triglyceride is another word for fat. Your book, for some reason, and there's, I'm sure, a chemical reason for it, calls it a triacylglycerol. Okay, too hard to say, too hard to spell. Triglyceride, basically the same thing. If you see it written down like this, do you think you could pick out that it's a triglyceride? I think you could too. So don't sweat it because they're the same thing. So if you take a look at the molecule right here, you'll see you've got the glycerol backbone and then 1, 2, 3 fatty acid chains attached. When each fatty acid chain attaches, it's actually going to squeeze out through a dehydration synthesis or a condensation reaction, a molecule of water. Just when any two things join, we're going to squeeze out some water. So I want to put this up here. Get this bigger. I'm going to put this up here and talk about fats. Triglycerides. Showing up. Yes. All right. We've got glycerol and 1, 2, 3 fatty acids. And then we have our glycerol backbone. Once again, dehydration reaction to attach each of the fatty acids and form a bond. You need to know the name of the bond. Just like in carbohydrates, the bond between two components was called glycosidic linkage. This bond, it's super interesting, it's called ester linkage. Interesting because look, ester starts with the letter E. What does a triglyceride look like? It looks like a letter E. Yay! I love it when it's so neat like that. So that's a triglyceride with 3 fatty acids. So let's talk a second about fatty acids. Fatty acids can be saturated or they can be unsaturated. The difference between the two is that saturated fatty acids have the maximum number of bonds or maximum number of hydrogens and no double bonds. So if we were to draw it, I'm just going to draw it and put it on the board just like I did in class. Okay. So this is a hydrocarbon chain with the maximum number, and it's bonded to some molecule over here that we don't really care what it is. But this is your fatty acid. Every single possible spot that could be bonded with a hydrogen has a hydrogen on it. There are no double bonds. So this is saturated. No double bonds. And these are solid at room temperature. And I'm going to also write as it cools or as temps cool. Okay, we'll get back to this in just a second. It will make sense why I brought that up. So let's talk about unsaturated. Unsaturated have at least one double bond They can have more. So if we were to draw it, it is still showing up. Turn it down just a bit. Okay. And it's some mystery molecule right there. You can see there's a huge number of differences in the number of hydrogens. In the saturated, there are more, and in the unsaturated, there are way less because of the double bonds. These are liquid at room temperature. What do we call liquid fats? Nobody says, I'm going to go get some liquid fat. We call them oil. So these are oils. And our oils come from plants and fish. Okay? I promised I would talk about why we care about the temperature thing in just a second. So just hold that thought. I'm going to minimize myself again. Excuse me. And go on down to the next slide. So when a fat is unsaturated and where the double bond is, you see right here, it causes a bend. I did not draw mine with a bend, but it does cause in nature, it caused the fatty acid to bend. So you see how it's got a kink in it. Put that in the vault, okay? These are straight, always, solid at room temperature. These are liquid at room temperature. We are getting to why we care, I promise. So phospholipids are what makes up our cell membrane. It's got the phosphate head and the fatty acid tail. And you know from studying your functional groups that the phosphate in the head has a negative charge. Because it is charged, it's gonna like the polar molecule of water. It's gonna really like hanging out in a charged environment. But the fatty acid tails, remember, are hydrophobic. They don't want to be near water. So what's going to happen if we literally dumped a whole bunch of phospholipids individually into a bucket of water? They would self-assemble into a membrane because the heads like water, the tails do not. They'd be like, ah, oh, this is safe. And they'd find a nice safe spot with each other with the head, excuse me, the heads outward. Okay, why do we care about this? Because in nature, our cell membranes, and this is the 2 units away, our cell membranes need to be kind of fluidy. I think, and we'll learn this in the unit, I think it's 10 to the 7th times per second, these phospholipids can switch places. So they're constantly moving around. Let me draw a phospholipid. In nature, think about the really, really cold weather. So I'm gonna just slide this down here. Totally improvising here. Here's your phospholipid, your 2 fatty acid tails, okay? If you have saturated fatty acid tails and the weather gets colder, things are gonna compact and solidify, okay? They're gonna get really tightly close together. But remember, we said our cell membrane needs to be kind of fluid. Let me ask you, ladies and gentlemen, when are you ever gonna be room temperature? We're not. We're going to be room temperature when we're dead. Okay? We are homeotherms and we maintain homeostasis. And no matter what the temperature is, it's 98.6 degrees. So we don't need to worry about our fats getting really compressed and solidifying as the temperature cools. It doesn't matter. Okay? What if you're a plant? What if you're a fish that lives under the Arctic shelf in the really, really cold water and it's 33 degrees? Okay? And you have a cell membrane that needs to stay fluid. You have been blessed with these kinky fatty acid tails that are going to prevent your cell membrane from compressing too much and solidifying. So that's why we really do care about the difference between saturated and unsaturated fatty acids in nature and in living things, because it makes a big difference in terms of the membrane and its fluidity. Additionally, we have cholesterol in ours that help to maintain the fluidity of our membrane. Animals don't need cholesterol. plants don't need cholesterol, animals do. And as a segue to cholesterol, we have right here these 4 fused rings. That is cholesterol right there. Okay. It looks different than all the other lipids. And also some of you are going, well, Miss Corcoran, you said that sugars are rings. Well, yes. If you recall how the polysaccharides look, they were long chains of rings linearly. If you take a look at this cholesterol molecule, you'll notice that it's 4 fused rings kind of clumped together. Okay, this particular molecule is a steroid molecule because it has some functional groups attached to it. And these 4 fused rings are consistent with cholesterol, which is a base of steroids. So we have to have fats in our body to make some of our sex hormones, which are testosterone, estrogen. Those are steroids. How are you going to remember that these fused rings right here, we don't really care so much about all the stuff hanging off. I mean, in life we do, but for our identifying the molecule on our quiz, we don't. 4 fused rings, steroids, cholesterol. Where else do you see, what do you honestly think of when you hear the word steroid? Like, honestly, we think of athletes or anybody trying to take their physicality to the next level. Okay. When would an athlete want to take their game to the next level? Okay, so this is how I remember it. Can you see that? Da, 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 da. Yes, I've just drawn Olympic rings. In no way am I saying all Olympic athletes do that, but I'm just telling you this is the way I remember it. 4 fused rings of steroids, Olympic fused rings, athletes, steroids, whatever. Take it or leave it. I'm always going to share my little brain things with you. But that is the end of lipids. If you have any questions, just let me know.